Okay, so the difference between the 3n particles in one dimension and n particles in 3 dimensions appears when you have the energy dependence on momentum is not in square. Because if it is squared, then in 3n dimensions, for one particle in 3n dimension, you have the sum of squares. If you have n particles in 3 dimensions, then you have 3n terms, each of which is a square. So nothing actually changes. But if you have, for example, as in the homework problem, if the energy is proportional to the momentum of the particle, then in 3 dimensions, it will be the sum of square roots of sum of squares, whereas in 1 dimension, it's just sum of numbers. So that is why, in this case, the 3n particles in 1 dimension and n particles in 3 dimensions are different. And then we just made a review of the density matrix. And along, we discussed some of the properties, like the elements of rho squared is smaller than rho if we have a mixed state, that is a state that cannot be written as that cannot be described by a single wave function. For example, this state over here, this one over here, is not a pure state. If you consider this, the first spin only, there is no single wave function describing the first spin. But still you can describe the same system using the density matrix. Whereas if you look at this one, the second state, in this one the first spin can still be described by a single wave function. Although there are, in both cases there are 2 spins, since the wave function of this 2-spin system are different, in the second one, the first spin is still a pure state. There is a single wave function describing the properties of the first spin. So the first wave function is also called an entangled state. You cannot separate the wave functions of these 2 spins. Whereas the second one is called an unentangled state. Basically because you can separate the wave functions of these 2 states, of these 2 spins. And then we went over what is the canonical ensemble. In the canonical ensemble, it's basically, all this formalism in terms of the density matrix, the main thing it tells us is that we can use whatever we did in the classical statistics as long as we stick with the energy basis. A simple example was a simple spin in a magnetic field in which if we choose a representation in which the Hamiltonian is diagonal. This is our density matrix, so we evaluated the density matrix. So this is our density matrix. So once we know the density matrix, we can calculate whatever we want about the system, like the expectation value of the z component of the spin. And in fact, this is a problem that we had already studied when we were discussing classical statistics, where we hadn't developed this quantum mechanical statistics, but the result is still the same. Basically because when we were treating this system before using our formalism of classical statistics, when we applied it over here, we stick with the energy basis. Now we looked at the density matrix of a free particle in a coordinate space. So it's basically this matrix. We first evaluated this matrix element. For the dense matrix elements of the density matrix, this is basically what we had obtained. Then we had defined this lambda. We didn't really discuss that lambda a lot, but in the convention of the book, at least, the definition is slightly different. The definition has a pi over here, so we will probably switch to the convention of the book in this lecture. Okay, any questions? Or any questions that you want to discuss before the exam? Anything you want repeated? Keep in mind that in the exam you still have one cheat sheet. Just prepare one page of cheat sheet, whichever formulas you think you will need. Any questions? Now let's switch to the quantum mechanics of indistinguishable particles. You see, we had already discussed to some extent this indistinguishable particles. You see, there is these two concepts, indistinguishable and identical. So these two things are different things. Well, identical particles can be indistinguishable, or they can also be distinguishable. In identical particles in classical physics, they are still distinguishable, because classical physics tells us that we can follow particles. We can follow their trajectory. So if we can follow their trajectory, that means we can basically distinguish them, because different particles will have different trajectories. So that's a way we can use, that's something we can use to distinguish various particles, although they are identical. But quantum mechanics tells us that identical particles like electrons, protons, neutrons, that we cannot distinguish them. They are indistinguishable. Basically because quantum mechanics also tells us that we cannot really track them. So that is something we have to incorporate into our discussion. Now, if you remember, we had already discussed to some extent this indistinguishability in the so-called Gibbs paradox. If you remember, when we were using this classical statistical concept, we had this problem. We had two containers separated by a separator. And if we remove that separator and allow these gases to mix, in our original formalism, the entropy increased. Whether the particles were identical or not didn't make any difference. But if they are identical particles, when we remove this barrier and later on put it back, the final state is the same as the initial state. So the entropy should not change. So this was the so-called the Gibbs paradox. And the resolution of this was we had replaced the number of states. We had corrected it by dividing it into n factorial. Now, where did this n factorial come? Well, because if you have two identical indistinguishable particles, if you just exchange their states, let's say, they shouldn't give a new state. So these number of exchanges, the number of ways we can exchange the states of particles, is basically n factorial. Not exactly though. So we have to divide this by n1 factorial, n2 factorial, n3 factorial, etc. n1 being ni being the number of particles in state I. So this should have been the correct factor, quantum mechanically at least. But in the Gibbs approximation, let's say, it resolves the Gibbs paradox. So in this mixing of these two identical gases, if they are identical, entropy doesn't increase. If they are not identical, entropy does increase after this correction of n factorial. But nevertheless, it is only approximate. It is correct in the approximation that ni is less than or equal to, let's say, 1. As long as ni is 1 or 0, then in fact the correction of dividing by n factorial is correct. So that basically means that there shouldn't be two particles in exactly the same quantum, in exactly the same microstate. Classically, that means same momentum, same point. So in that approximation, Gibbs correction works. But especially in low temperatures, for example, this approximation does not hold. So we have to take into account that Ni can be larger than 1. And that is where quantum mechanical effects come into the game. Now, first, let's discuss how we describe non-interacting identical particles quantum mechanically. Well, since there are no interactions, the Hamiltonian of the system can be written as the sum of the Hamiltonians of, let's say, Pi and Qi, corresponding to each one of the particles. And the Schrödinger equation will be I h bar del over del t psi, no, not E, is equal to h of psi. Well, if you look in the Hamiltonian, various coordinates, they don't come together, they don't mix. Each term contains only the coordinates of a single particle only, not their products. So this tells us immediately that we can solve this problem by separation of variables. For a given time-independent Schrödinger equation, let's go for that. This is h psi for a given energy E. So psi E, we can write this as, well, this will be a function of all the coordinates Qi. This will be equal to U1, let's say Q1, U2, Q2, Q1. We can just write it in this form. And each one of these ui's should satisfy this equation. Hi of ui should be equal to epsilon I of qi, no, ui of qi, ui. And the energy of the combined system will be sum of this epsilon I. Of course, the various u1, u2, u blah, blah, those functions can be the same functions also if the two particles are in the same microstate. Well, we have already solved it, the Schrödinger equation for non-interacting particles. If we know the single particle solutions, ui's are the single particle solutions. But now there's a different problem though. We had already said that if the particles are indistinguishable, if we just exchange two of them, nothing physically should change. This basically amounts to saying that the probabilities should not change under the change of these particles. So P is a permutation. Some arbitrary permutation. Well, I mean, we will be using some notations about the permutations. Let me just clarify some of the notations for permutations. Usually, okay, for example, we denote permutations in this form. For example, this is a permutation of two numbers. It just, instead of 1, it puts 2. Instead of 2, it just puts 1. It just exchanges 1 and 2. Another permutation can be 1, 3, 5. This is another permutation. So this is, instead of 1, it puts 3. Instead of 3, it puts 5. And instead of 5, this permutation puts 1. It doesn't do anything to 2, it doesn't do anything to 4. So these are permutations. The first one is a permutation of at least 2 numbers. The second one is a permutation of at least 3 numbers. Well, it can be more. I mean, if a number is not shown in the notation of a permutation, then that permutation does not change that number. Now, if you look at the last one, I can write it also in this form. So this is just the product of two permutations. And you just apply those permutations successively. You see, if you look at this one, the first permutation, instead of 3, it puts 1. The second permutation, instead of 1, it puts 5. So this combined permutation just replaces 3 with 5 as the initial as this permutation. If you put 1, the first permutation puts 3 in terms of 1, and the second permutation doesn't do anything to 3. So this combined permutation just replaces 1 with 3 as the initial permutation. And if you look at 5, the first permutation doesn't do anything on 5. The second permutation, instead of it exchanges 5 and 1. Instead of 5, it just puts 1. So it is just as the initial permutation. So these two this product is equal to the initial permutation. So you see, this permutation I can write as the single permutation of two numbers. Here, it is two permutations of the same number. It can be written as the product of two permutations of two numbers. Now, the signature of a permutation is just -1 to this number, 1. This is how we define the signature of a permutation. So in the second case, let me call this 1, 2, signature of P2 is equal to -1 to the power 2, which is 1. Now, of course, there are different ways of writing a given permutation as products of these basic building blocks, but still the signature does not change. P2, I can write it as the product of 4 basic permutations. This is the same thing as 1, 5, 1, 3, 2, 4, 2, 4. So the number is kind of trivial, but the last representation is kind of the product of 4 different basic building blocks. So this P2, I can write it as product of 2 building blocks, or 4 building blocks, or 6 building blocks, etc. But nevertheless, it will always be even or odd. So that doesn't change. That's the property of the permutation itself. So that property is called the signature. Okay, now let's go back to our discussion. So here we said that P psi, permutations of psi of this is a function of Q1, Q2, Qn. Well, let me first use a simplified notation. Rather than writing Q1, Q2, Qn, let me just write psi 1, 2, n. To save ourselves from writing the Q. P of psi is just psi of P1, P2, Pn. P1 is what the permutation takes 1 to. P2 is what the permutation changes 2 into, and Pn is what the permutation changes n into. So let's say this fact that for indistinguishable particles, the physical properties of the system should be the same under the exchange just tells me that if I permit the coordinates of 2 functions, 2 arguments of my wave function, the magnitude of the wave function should not change. Just the magnitude shouldn't change. Well, the phase can still change. But you see, if you apply, let's just take a simple example of P being 1, 2. A simple case. Just exchange two particles and nothing more. It doesn't have to be the first and the second particle, it can be just any particle you like. Let's say P psi is equal to e to power I alpha psi. I exchange 1 and 2, and the wave function can get an overall phase. Let me apply P once more. This is P acting on e to power I alpha psi. This is e to power I alpha P of psi. This is e to power I alpha squared psi. So each permutation, just under each permutation, my wave function acquires this phase e to power I alpha. So if there are two permutations, it's just e to power I alpha squared. But at the same time, P squared, which is 1, 2, 1, 2, is identity. It doesn't do anything. Because first time I just exchange 1 and 2, the second time I exchange 2 and 1. So I'm back to my initial arguments of the wave function. So this tells me that psi should be equal to e to power I alpha squared psi, or e to power I alpha should be plus or minus 1. So the wave function of identical particles should either be symmetric or anti-symmetric, indistinguishable particles. So that is one thing I have. Well, let me just put one remark. It doesn't work in 2 dimensions. Due to some topological properties of 2 dimensions. You see, in 2 dimensions, the problem is, let's just assume we are physically exchanging the position of 2 particles. You exchange it once, and then you exchange it again. Basically, the particles are following some, at the end of these 2 exchanges, the particles had followed a circle. A circle is not a trivial operation in 2 dimensions. Because if you take a point out of the 2-dimensional plane, you cannot deform that circle to nothing. In 3 dimensions, you can do it, even if you take a point out. So this argument doesn't really work in 2 dimensions, and hence in 2 dimensions, we have what are called anyons. Okay, so just there is such a thing in 2 dimensions. Keep that in mind. But we are now at least interested in 3 dimensions. Now, which particle has which sign? It turns out, I mean, if you take a field theory course, you will probably see the proof that fermions which are particles with spin a half integer, like the electron is a fermion, helium-3 is a fermion, proton is a fermion, neutron is a fermion, and their wave function is antisymmetric. And bosons, they have integer spin their wave functions are symmetric. So our previous argument told us that the wave function of a system of indistinguishable particles should be either symmetric or anti-symmetric. It doesn't really tell us for which particle which systems it should be symmetric, for which systems it should be anti-symmetric. And this fermions and this what's called the spin statistics theorem relates the spin of the particles to whether their wave function should be symmetric or anti-symmetric. It turns out that for fermions, their wave function should be anti-symmetric. For identical bosons, their wave function has to be symmetric. Examples of bosons are photons are bosons. They have spin 1. Helium-4 is a boson. Helium-3 is a fermion, but helium-4 is a boson. Pions are bosons. There are many, all mesons in particle physics are bosons. And the name of, in this case, in the two-dimensional case, anyons is these only. Okay, so how do we construct their wave function? We already had, in our previous discussion, we said that, okay, we have this Hamiltonian of the whole system is just the sum of the Hamiltonians of individual particles if they are not interacting. Then the solution can be written as a product of each one of the solutions of single particle Schrödinger equations. But it's neither symmetric nor anti-symmetric. But we also know that if there are more than one solution to our equation, if we obtain more than one solution using separation of variables, we should then just sum them up. And for the symmetric wave function, we can obtain from, let's say, U1, 1, U2, 2, UN, N. Well, you see, we just need to sum different terms that we obtain by permitting the different particles. So instead of 1, I will add P1, P2, Pn, and sum over all possible permutations with some normalization constant. This is a symmetric wave function. Basically, if we apply some permutation to this one, let me say P prime, it's a constant over times the sum over P, U1, P prime P1, U2, P prime P2, UN, P prime Pn. This is a constant. You see, as P runs over all possible permutations, P prime P also sums over all possible permutations. So instead of summing P, I can sum over all P prime P. But P prime times P is a permutation itself. I can just rename it's now a dummy variable. I can just rename it. Sum over all P's, U1 P1, U2 P2, UN Pn, which is nothing but my initial wave function. So this a wave function defined in this way is a symmetric wave function that is suitable to use for bosons, sorry. Now for fermions, it has to be anti-symmetric. Well, the wave function we can use is basically has more or less the same form, But we just need to make a single correction to take into account the sign. This is anti-symmetric now. This delta P is called the signature of P. So it's anti-symmetric under the exchange of two. Well, if you apply some permutation on that, this will be equal to, well, we basically repeat exactly the same arguments. This is constant. Again, instead of summing over P, I can sum over P prime P's. But then here P prime inverse, this will be the signature of P prime inverse P. But the signature, keep in mind, is -1 to the number of these basic blocks in the in a representation of the permutation where it is written as the products. So if you multiply two permutations, then the number of building blocks that appears when you write that product as the product of these basic blocks is just the sum. So the signature is just the signature of P prime inverse times that constant but this is nothing but our psi A, and the signature of the inverse is nothing but the signature of itself. So this is what we wanted. When we apply a permutation to this anti-symmetric wave function, then that wave function is multiplied by the signature of the permutation. If it's just the exchange of two particles, then that signature is -1, and that's what we wanted. So now we have the wave functions to describe all these systems. Before passing on, if the UIs are properly normalized, then this constant is just 1 over the square root of n factorial. It's just when you multiply them, there will be n factorial contributions. So to get the proper normalization of the combined system, you just divide by 1 over n factorial. And one last remark, this psi A, well, you can also write it as a determinant. It's just the so-called Slater determinant. Now, when you calculate that determinant, it already takes into account these plus and minus signs. So now we know how to write these matrix elements. Now the next thing is how eventually we will be counting these microstates, number of different matrix elements we have. But rather than writing all these wave functions, another way we can use to show these wave functions is to specify an I. Number of particles in the state UI. Well, because they are indistinguishable, the question which particle is in which UI doesn't really make any sense. So once we know the number of particles in the state UI, we know the wave function, or we know the microstate of the system. So in a sense, counting the microstates would correspond to counting these possible different ways of specifying an I. Subject to various conditions, of course. We have the total number of particles is n, if we are in the microcanonical ensemble, let's say, and the total energy of the system is Ni epsilon I, which should be equal to E. These should hold in this quantum mechanical description, because we are looking for a wave function describing a system with energy E and number of particles n. When we go to microcanonical ensembles, these will appear as constraints on our system. Any questions? Now let's calculate the density matrix for n non-interacting particles. Well, for simplicity, in your book there is a discussion for an arbitrary n. But just for simplicity, let's stick with n is equal to 2. Because when you try to do it for arbitrary n, there are technical complications. The notation becomes kind of obscure. But I don't think there's too much more insight. So let's just stick with n is equal to 2. So we are looking for this matrix element. Let's look for partition function, not the density matrix. Well, partition function will be just the integral of this over R1 and R2. And this is equal to R1, R2, rho, R1, R2, no, not rho. Now, since we are looking at the partition function, I need this one. So this matrix element, I can just insert some energy eigenstates, a complete set of energy eigenstates. Of course, there is the sum over all psi e's. And so this is equal to sum over all psi e's, e to power minus beta e, R1, R2, Psi E R1 R2. Now this one, Psi E R1 R2 is nothing but U1 1 U2 2 plus, let's say, A U1 2 U2 1. And if we want to normalize it, this is 1 over square root of 2. Now A is 1 for bosons, minus 1 for fermions, and 0 for Maxwell-Boltzmann, let's say Maxwell-Boltzmann. Before we had always taken A to be 0. So we didn't symmetrize or anti-symmetrize. So if you go back to our matrix element, R1, R2, R2, R1. Okay, so we are summing over all our wave functions, e to power minus beta e, or let's say epsilon 1 plus epsilon 2. Here this wave function is, well, there is 1 over square root 2 for both of them. Let's just put 1 over 2. U1, 1, U2, 1, U2, 2, plus A, U1, 2, U2, 1, multiplied with U1 star 1, U2 star 2, plus A star. A is real. U1 star 2, U2 star 1. Now, what are these wave functions? We are summing over all microstates. What are we actually summing on? Let's also specify those. So we will be assuming that our particles are free within a volume. So Ui of, let's say, Ri, this is just 1 over square root of V e to power I Ki times Ri, where this Ki will be 2 pi over V to the power 1/3 times Ni, where these Ni's are just 3 numbers, Nx, Ny, and Z, and these Nx, Y, and Z's are 0, plus minus 1, plus minus 2, etc. So summing over all microstates would basically amount to summing over all these Nx, Ny, and Nz's. Let's say N1, N2, times 1 over 2 Okay, so when we take that product, we will have 4 terms. So what do we have? U1, 1, U1 star 1, U2, 2, U2 star 2. This is the product of the first terms in the parentheses. Plus A, U1, A squared, U1, 2, U1 star 2 times U2, 1, U2 star 1. This is the product of the last 2 terms. Plus A, U1, 2, U2 star 1, U2 star 2, U2, 1, U1 star 1. This is the product of the second term in the first parentheses and the first term in the second parentheses. Plus A. Okay, so the first term, U1, 1, U2 star 1 times U2, 2, U1 star 2. This is the first term in the first parentheses and the second term in the second parentheses. So this is my matrix element. Now, what we are interested in is the partition function. Or let's see, eventually we will calculate it, but not yet. Well, you see, here we are summing over all the momenta. And U1 and U2, they basically differ by their momentum. But consider this term and this term, these 2 terms. Well, if you look at those 2 terms, the third, if you exchange K1 and K2, the third term becomes the fourth term, and the fourth term becomes the third term. Well, we are summing over a particular value of K1 and K2, and also the other way around. So when we sum over K1 over all the momenta, the fourth term and the third term, they basically give the same result. So I can just sum them up. And this just becomes 2. Well, the same holds for the first term and the second term. You see, the first term and the second term, if you look at them, if you just exchange K1 and K2, the first term becomes the second term becomes the first term. So instead of just treating them separately, I can just sum them up. So this becomes 1 plus A squared. So this R1, R2, e to power minus beta h This is equal to e to power minus beta epsilon n1 plus epsilon n2 1 over 2 u1 1 u1 1 u2 2 u2 2 plus a 2a u1 2 u2 star 2 u2 1 u1 star 1. Well, let me rewrite it in a slightly different form. So the first term is, there is the 1 over 2, there is 1 plus a squared, there is e to power minus beta epsilon n1, u1 1, u1 star 1, times e to power minus beta epsilon n2, u2 1, u2 star 1, plus 1 over 2, 2a, e to power minus beta epsilon n1. Keep in mind, I'm summing over momenta. So I can just group the terms that have the same momenta that I'm summing over. So the second one is u1 of 2, u2, u1 star of 1, e to power minus beta epsilon n2, u2 of 1, u2 star of 2. Now they are just different particles. I mean, no, a single particle matrix elements. So this is equal to 1 over 2, 1 plus a squared. The first one is R1, e to power minus beta h1, R1, times R2, e to power minus beta h2, in the first term I made a slight mistake. This is 2. Plus 1 over 2 times 2a R2, e to power minus beta h1, R1, times R1, e to power minus beta h2, R2. Now let's consider bosons and fermions only. Well, this means that a squared is 1. That's why I'm restricting myself to bosons and fermions only. You can keep a to be arbitrary if you like. For the so in this limit, R1, R2, e to power minus beta h, R1, R2, in this, not in this limit, but in these cases, this is equal to R1, e to power minus beta h1, R1, R2, e to power minus beta h2, R2, plus a R2 beta h1 R1 R1 e to power minus beta h2 R2. Well, these we had already calculated. yesterday. So this, at least for the point that I would like to reach, we can simplify it already. If you remember what we had obtained yesterday, is that this R1 e to power minus beta h R2, this is equal to R1 e to power minus beta h R1. This is just position independent term times e to power minus beta minus e to power minus R1 minus R2 squared divided by lambda squared. This is the exponent is the position dependent term. It only depends on the separation. Well, that's not a big surprise. Basically, what we are interested in is we are looking at a free particle. There is no special point. So the only thing that it can depend on is the separation of these 2 points. So with this, keeping this in mind, this R1, R2, e to power minus beta h, R1, R2, this is equal to R1 e to power minus beta h1, R1 squared times 1 plus a e to power minus R1 minus R2 squared over lambda squared. And keep in mind, A is plus for bosons minus for fermions. Now, what does this tell us? Let's just remember what this was. This is basically the probability density that there is a particle at the point R1 and another particle at the point R2. The diagonal entries of the density matrix, they give us the probabilities. Now, if you look at that probability that we had calculated, of course we have to go ahead and normalize it. So in our case, this probability is equal to some constant, meaning that independent of R1 and R2, multiplied by 1 plus or minus e to power minus R1 minus R2 squared over lambda squared. And I repeat, these are non-interacting particles. Now, if you look at the densities, as a function of their distance, where this d, well, not, let's say not d, but let me just write R1 minus R2 squared over lambda squared. When that is 0, when that goes to infinity, both of them go to the same number. They have the same asymptotic form, asymptotic value. But when that number goes to 0, that's their separation for fermions, that that this matrix element just goes to 0. If the exponent is just 0, e to the power 0 is just 1. 1 minus 1 is 0. So this is the asymptotic value. This asymptotic value is, by the way, 1 over v squared. If you put in that constant. And then for fermions, it goes to 0. Whereas for bosons, you see that number is 1 plus 1, it becomes larger. Kind of the fermions, they try to avoid each other, whereas bosons, they kind of attract each other. But keep in mind, there is no interaction. There is no force. They are not exerting any force on each other. Now, this is also sometimes called the quantum mechanical force. There is no force in the sense of let's say the electromagnetic force, or I don't know, gravitational force, etc. There is no such force. Nevertheless, they influence each other because of their quantum mechanical properties. If you like, you can still treat this, let's say, this correlation, let's say, attraction or repulsion, by defining a force, and that, if you would like to define some kind of a potential energy, let's say, you can define a potential energy to take into account this correlation, and it should be such that it should take into account this term over there. This is just minus kT logarithm of whatever this is. Then if you just define such a potential, then still you can have some kind of you can take into account the correlation just treating the system classically. This, let's say, an effective way of taking this correlation force into account. Well, if you are following gravity, for example, I'm not such an expert on it, but my understanding is that there is Verlinde's, let's say, hypothesis for the time being, that maybe gravity is not really a force, but a statistical entropic force, let's say, like this one. In this one, there's no force to understand. There's no fundamental force. It's just a quantum mechanical effect. Quantum mechanical plus statistical, let's say. And Verlinde proposes that maybe gravity is also such a force. Not a force that exists at the fundamental level, but maybe it's just a statistical force. Okay, any questions? Okay, let us also end here for today. I mean, I do advise you to go over the derivation in the book also for an arbitrary number of particles. The result is basically the same. It's just, instead of 2, you have many more particles. The treatment just kind of becomes quite technical. And so now we know how to treat the identical particles also. The next thing we need to do is, okay, apply it. Quantum mechanical gases. How do they deviate? How do we treat the quantum mechanical gases? Because you see, in the quantum mechanical treatment, the main problem will be how do we take into account these terms, these factors? Because the counting will be kind of complicated. But we can still do it. And that is what, well, I mean, today you have the exam. These are, of course, not included in the exam. But next week we will just go into discussing the quantum mechanical gases. And then, okay, we will first discuss them generally. Then we have the boson gases, the fermion gases, and That will be the end of the semester. Yes, questions? So see you in the exam.